Okay, it's time to proceed with the next talk by Professor Yaakov Malinovsky from University of Maryland. He will tell us about hitting a prime in 2.43 dice rolls on the average. Thank you.
Thank you. First of all, thank you for inviting me to give a talk. My pleasure. And so I'm going to talk about hitting a prime in 2.43 dice rolls. This is joint work with Noga alone. So the work related to puzzle, which appeared in the bulletin of the Institute of Mathematical Statistics in 2017 by contributing editor Anirban Dasgupta. And the puzzle is following. Suppose we're tossing a dice, and it's fair dice, and xi, x2 is outcomes, and we looking when first time the sum of outcomes is hitting the set of prime numbers. So let's denote by tau its minimum discrete time when some of the dice outcomes hit the set of prime numbers. Now, the contributing editor mentioned in the bulletin that lower bound of expected hitting time is a 2.3479. Heuristic approximation of expectation of average hitting time, it's about 7.6. And he also mentions that it is not known if variance is finite or not. So in this work, we will show by pretty simple calculations that exact value of expectation is much closer than to lower bound than the two approximation which was given. And also we will show that variance is finite, and also will calculate its value. And I will show how we will proceed. So, but first of all, I will show numerical outcomes from the simulation. Suppose we imitate Monte Carlo simulation on computer, and suppose if we're doing 10 million times, average hitting time, it's about 2.4286. Variance of hitting time, it's 6.2463, and maximum value of tau among 10 million simulations is 65. So it says that we should be, it's not a maximum, it's not running to the tail very fast. So seems like it's possible. It seems like this number should be reasonable. So we proceed with recursive algorithm to calculate. So expectation and variance we can present, since discrete random variable, we can present expectation as sum of probabilities at hitting time more equals k, from k starting from 1. And second moment, we can also present in similar manner. So what we will do now, we will calculate exactly by recursive relations, first, for example, 1,000 terms in each sum, and then we will bound the remainders. So, and we're doing it in the following way. So we're going now to figure out how to calculate this probability recursively. And in the following way, it's following. So if we're looking on the discrete time k, at time k, sum of outcomes can be between k to 6k. Since each time dice, it's 1, 2, 3, 4, 5, 6. Now, let's denote by pkn a probability that at time k, a sum of outcomes equals to n it's non-prime, and also all partial sums up to time k also not prime. It means if we need to calculate probabilities at hitting time more equals k plus 1, it means that up to time k, include k, it was no prime. If we intersect by law of total probability, if we intersect with all possible values of n, it's exactly probabilities we're looking for. Now, what remains is calculate pKa using recursion. And what we're doing, we simply define recursive algorithm for computing pKa precisely. So, and for practical purpose, we're doing it for first 1,000 terms. So for time 1, non-primes, it's 1 for 6 with probability 1/6. And when for each time k from 2 to k, and when the total at time k can be between k to 6k, pKn can be calculated using law of total probability, simple by conditioning on previous step, such that at time k minus 1, total it's n minus I, when I running between 1 to 6, and n minus I no prime. Simple law of total probability. Now, if we're coming back to exact calculation expected time, we divide it by 2 pieces, a first k term, and then rest from k plus 1 to infinity. And using recursive formula, we simply calculate for 1,000 term this quantity, ek, for k equals 1,000, and it's come out exactly what simulation says, 2.4284 and so on. Now, what is remains, we will show now that remainder, it's below 7 times 10 to power minus 8. Very small remainder, even by rough calculations. With respect to variance, we proceed exactly in the same way. We calculate first part of second moment, and then we bound the second part. So when we divide variance by 2 pieces, when first piece calculated based on first 1,000 terms, it became exactly what we obtained in simulations, 6.24. And remainder, we will show that bound it's 10 to power minus 4. So now what is remains to show how we bound 2 terms. So this result, what we're going to bound these 2 terms. And now, so first proposition says following: for every k and every non-prime n, remember a pkn that at discrete time k a sum of outcomes of dice equals to n is non-prime, in all partial sums also non-prime. This probability can be bounded by this quantity where pi n is number of primes smaller than n. Now it's done, so the proof of this proposition is done using the induction on k. So for k equals to 1, it's easy to check. And then now what we need to do is from step k minus 1 to come to step k. So, and we're doing it by 2 steps. So let's look on the set n minus 6, n minus 5 to n minus 1. And supposing this set we have q primes. From it immediately follows that number of primes for each I 1 to 6, number of primes which less than n minus I plus number of primes in this set always more equals the number of primes up to n. And now by using general formula and by induction and then what we already obtained in recursion by using law of total probability, now induction step provide us this quantity, and then this inequality provide us second inequality, and we finish induction step and we prove the proposition. Now to make it more simple, so here it's pi n, but it's well known to make it more simple that by prime number theorem for for the large n, for example, here, let's take n more than 1,000, number of primes less than n, it at least 0.9 times n over ln n. Therefore, simple substituting in the proposition pi n, we obtain following inequality, immediately corollary. And now we can apply this to found the remainder term. Now let's recall that probability that tau more than k plus 1. It's exactly sum of these probabilities of pkn when n running for different values of n, such as n running at discrete time k between k to 6k. And now using the following above proposition, we directly calculated, applied this inequality for pkn and obtain following upper bound. Now this upper bound, it's let's call it's sum of user notation. So this function only inside of some function I call fn. And now we will show now that how to bound this function. So it's done in following way. This function fn, we only interested for integer n larger than 1,000. We figure out that it has unique maximum at the point 1049. And when simple looking by steps of the 13 ln n, we found it has geometric decay. And using simple geometric decay series, we obtain upper bound. Now, with respect to the variance term, remainder term, it's exactly the same, little bit more steps in calculation, but we obtain exactly the same way. We obtain upper bound of remainder term 1 over 10,000. Now, there is a few extensions recently appeared to this work. Recently, Lucy Martinez and Doron Zilberger extended using symbolic computation in several directions. First of all, they consider dice with M faces, and it provided very nice tables of very fast calculation using symbolic computation. Now we considered the cases when one would not necessarily needs to start at 0. And we also considered the cases when there is other properties of natural numbers, not just in prime numbers. Also recently, in very nice work, Shane Chern found very nice asymptotic result of expected heating time. Suppose we have M faces, and it's fair dice, and we count until sum of outcomes hit the set of prime numbers. He found that expected value of heating time has order ln of n, and it's generally done by by 2 steps, but remainder step he used very detailed proof to found proper formulas for remainder step. And this is all. I think I'm on time. Thank you.
Thank you very much for a very nice talk.